Section is fuel metering and in-cylinder air fuel motion. So in this section, I'm going to look at how the air fuel mixture is prepared in spark ignition engines and the way the fuel is injected in diesel engines, as well as how the air fuel mixture or air moves within the cylinder, particularly during the intake stroke and in the compression stroke. Now, as far as the combustion process is concerned, one of the most important things, important fluid mechanics phenomena that we expect during the in-cylinder flow is the turbulence. So we expect certain degree of turbulence in this mixture motion in order to enhance mixing process, mixing of in fact air and fuel as the gases move within the cylinder. So as I said, adequate mixing is essential for the proper combustion, because the engines rotate at very high speeds, at least 1,500 revolutions a minute or more. So the time available for this mixing process is very small. So we'll have to do this at a very quick time interval. For direct injection engines, particularly diesel engines, of course, we introduce fuel at the end of the compression stroke. Therefore, we don't have much time for mixing the fuel with the air. So the mixing is mostly governed by the momentum flux injected fuel. So the fuel momentum of the fuel particles being injected would govern the mixing patterns. That needs very high injection pressure. You have to forcefully spray the fuel into air, and that needs expensive injection system. And also, to enhance this mixing, as you inject, you could create certain turbulent, you could create certain flow fields, particularly the rotational flow of fuel, which is called swirl. Now the problem is, if you increase swirl, of course the volumetric efficiency decreases, and at the same time the heat losses will also increase. So these things I will describe as we go. As far as the fuel metering in spark ignition engines is concerned, now what is meant by fuel metering is mixing the right quantity of fuel with the air. So as I said in one of the previous lectures, so in early days in spark ignition engines, the carburetor is used for this purpose, and which was invented by a German engineer, Me508 in about 125 years ago. And this carburetor had been used in internal combustion engines or commercial engines, commercial spark ignition engines up until about 1980s. And still the carburetor is used for small size engines, but not mostly automobile engines that we use today. And I explained the carburetor, the basic operation of carburetor earlier, so I'm not going to go into details of operational aspects, but of course we'll go into a little depth on the fluid mechanics aspects. So for the completion of the discussion, I have included a few notes on the operation of the carburetor as well. Now, as I said earlier, if you look at the fluid mechanics aspects of fluid motion within the carburetor, now this is a schematic of a carburetor. So this is fuel system, and this is the converging diverging tube, and the fuel is introduced at this point at number 2. Air comes from number 1, and the air fuel mixture leaves at number 4, and the atmospheric conditions are represented in this particular diagram as infinity, P infinity, T infinity, and pressure and temperature under atmospheric conditions. Now the mass flow rate at point 4 is obviously mass of fuel and mass of air. Mass of fuel is introduced over here, and the mass of air is coming from the intake system. Now, if you assume this air is ideal gas, and the flow through the carburetor, you could represent using this relationship. Of course, this is from the ideal gas equation and orifice flow equation. T infinity is atmospheric pressure, gamma is specific heat ratio, C infinity is speed of sound in atmospheric air, which is of course equal to square root of gamma RT, T of course T infinity, and rho is the density, and AA is the cross section area at number 2. Of course, blockage by the nozzle as well as the boundary layer effects. The real flow area will not be the effective flow area through the orifice. So, accommodate those losses, we use discharge coefficient, which is always less than 1 for these reasons. And the flow through the nozzle, fuel nozzle, we can model using the same set of equations like this, where cross-section area again has to be multiplied by a discharge coefficient to accommodate the losses. In this case, it is around 0.75. And if you consider the critical flow conditions or choke flow conditions, mass flow equation under the choked condition can also be represented like this. And this critical flow also quite important for us when it comes to sizing the carburetor. Now, to decide the geometry of the carburetor, we define a parameter carburetor demand, which is a ratio of airflow to the airflow under critical conditions. Accordingly, dV is of course always less than or equal to 1. So the airflow ratio, we can write down an equation by combining all the equations that I just showed you previously. Mass flow rate of fuel divided by mass flow rate of air. I'm not going to go into derivatives, but you can combine the equations and find this. And carburetor demand is of course can be found by using this equation, assuming gamma is 1.4, which is a reasonable assumption for air. So these things you can find in here appendix C. And if you plot the carburetor demand for air, against air fuel ratio, as you can see here, under standard conditions, this is atmospheric conditions, and you can see the variation of carburetor demand against air fuel ratio for 3 different ratios of cross-section area of fuel flow divided by cross-section area of airflow. And you can see in a wide range, for example, from carburetor demand 20% to 80%, you can see this airflow ratio remains more or less constant. So that is a very encouraging observation, because in this region of fluid flow velocity, so this carburetor demand is more or less related to the flow of air. So as you know, the engines are operated in a wide range of speeds, so the airflow velocity also changes depending on the speed of the engine. Therefore, for carburetor demands 20% to 80%, or in other words, a wide range of airflow velocities or mass flow rates, you can have nearly a constant airflow ratio. So, by picking the correct ratio of AF to AA, we can design a carburetor to deliver a stoichiometric air fuel ratio, for example, in a wide range of speed conditions. So that is more or less one of the most interesting design observations of a carburetor.
If you have any experience in carburetor jet adjustment of your motorbicycle or lawn mower or any small size petrol engine, what this Basunais do is they change this area AF, that is fuel flow area, by adjusting the adjuster nut of the carburetor. So that is they call jet adjustment. And accordingly, you can move this graph up or down. Mostly, they tend to increase their fuel ratio so that you can produce more power. And at the same time, when the carburetor demand approaches to 1, that means the flow is becoming a critical flow or the choke flow, then air fuel ratio significantly getting increased. So that is what we do mostly at the cold start. When you pull the choke, what happens is the flow becomes choke, and this mass flow rate is approaching critical mass flow rate or more than critical mass flow rate. The carburetor demand becomes approaching to 1, then you get a rich air fuel mixture. So this is fuel air ratio. Increase of fuel air ratio means it becomes a rich mixture, rich of petrol, so that the cold start will be facilitated.
The carburetor is more or less obsolete in most of the modern automobile engines, IC engines. Instead, as I said earlier, what we use is fuel injection systems. So, as I briefly explained in one of the previous lectures, of course, there are 3 different types of injection methods, 3 different generations, I would say. Initially, the injection technique that we used was the throttle body injection, and then the injector nozzle brought close to the cylinder, and such a system was called port fuel injection. And then nowadays we use mostly direct injection technique in spark ignition engines. So if you look at the picture, you can see this is a port fuel injection and this is direct injection. And in the case of direct injection, you can see some difference in the piston crown. So the shape, there's a specific shape here to guide this fuel flow towards the spark plug to make the ideal mixture at the spark plug to initiate the combustion. So this fuel injection system was first patented in 1970s after heavy research and development work, and started using in the commercial vehicles in early 1980s. And the port fuel injection system is the widely used system, widely found system right now. That is, of course, fuel is injected right over to the intake valve, where you expect some cooling. As a result of that, we can vaporize fuel. And of course, even though this is the most commonly used system, now people are moving towards direct injection for many advantages, which we will discuss during our section on combustion. Now, fuel injection in spark ignition engines. Of course, if it is a port fuel injection, we do it outside the cylinder. That is done at a very low pressures comparatively. It's about 2 to 5 bars. And if it is a direct injection engine, of course, the injection continues through the compression stroke as well. Accordingly, the pressure has to be maintained up to about 130 bars. And Twin nozzle fuel injector is commonly used in spark ignition engines, where this nozzle opens up for fuel to flow as it moves up. This upward movement is facilitated by a solenoid valve, by an electrical signal through a solenoid valve, I would say. And of course, the electrical signal is usually a square wave pulse signal that we get from the computer. And the opening and closing time is very small because of this magnetic operation. So there are three direct fuel injection methods used in commercial engines. One method is spray guided mixing. There is a special shape made in the piston, hole in piston we say, and the injector is right at the top, and the spray is guided towards this shape in the piston. And most important thing is you'll have to have the right mixture at the spark plug in order to initiate the combustion. And the next type is called the wall guided swirl mixing. That is the rotational flow field of the incoming air helps mixing process, particularly creating the right mixture at the spark plug to initiate the combustion. So this also in here also there's a special shape made on the piston crown. The third type is wall guided tumble mixing. That is tumble flows. I will talk about tumble flow patterns soon. Guide the mixing as well as creating the right mixture at the spark plug. Now, if you look at the mass flow rate through the injector in a little more analytical manner, of course, it's a time integration of mass flow through the nozzle, and mostly the variable quantity, the time dependent quantity is the flow area, cross section area of the flow, and of course, this time dependent flow area we represent as an average quantity, average flow area, as you can see here. And of course, the mass flow through the nozzle is represented using this average flow area by the help of discharge coefficient, because always the real area is not the effective area for flow. So this delta P is the difference between the fuel delivery pressure and air pressure, the upstream throttle. As you can see in this graph, this is fuel per pulse in milligrams versus pulse width, and the flow is always, as you can see, the flow is linearly related to the pulse width. So if you need more fuel, then all what you need is to manipulate the pulse width. So the pulse width, change of pulse width gives you the right quantity of fuel, and that is you can see in this graph for three different injection pressures. So it's a linear relationship, so that we can simply increase the pulse width to get more fuel flow. Usually we keep the injector open depending upon the speed of the engine, of course, from about 1 to 10 milliseconds. That is the time per injection. And of course, it's very important to vaporize this fuel as you inject. Otherwise, there will be a layer of fuel on the intake system, particularly in port injection, which will cause cylinder by cylinder variation of combustion, as well as uncontrollable changes in the air fuel ratio. If I move on to diesels, of course, as I introduced earlier, there are two different injection systems we use: direct injection and indirect injection. As you can see here, the direct injection is um, directly injecting fuel onto the combustion chamber, the piston, and there's a special shape made in the piston. In the indirect injection, of course, there is a pre-chamber created in the injection system, where the injection taking place at this pre-chamber, and the burn gases goes into the piston. Now, as you probably know, the diesel is self-ignition system. Therefore, these gases should be ignited quickly. Combustion duration is much. The fuel injection system has been developed for rapidly formed combustible fuel air mixture. So, in direct injection method, so usually in diesel injection systems, the fuel is injected when the piston comes close to the top dead center in the compression stroke. So the pressures are very high. It's in the range of about 50 bars at a temperature nearly over 800 kelvins. And so to inject fuel at that high pressure, we'll have to have an injection system which could inject fuel around very high pressures, around 1000 bars, and the spray velocity is around 100 to 200 meters a second, because you'll have to create droplets so that quick mixing taking place for combustion to start. And using the same equations as I showed earlier, we could represent the mass flow rate through injectors using relationship which is a function of pressure difference as well as the cross section area. So in this one, of course, mass flow rate is represented as a function of speed as well, and delta theta is the combustion duration in terms of crank angle rotation. As you can see in this equation, if you want to inject the same amount of fuel at different speeds with same delta theta, that is same injection time, then of course we'll have to change pressure at different speeds. Injection pressure has to be changed. So accordingly, we find the injection pressure is proportional to delta P and square of speed. And if an engine operates in a wide range of speeds, like maximums, the ratio of maximum speed to minimum speed, for example 5, and we get injection pressure ratio at these two different speeds around 25. And that means if low speed injection, if you inject fuel at 50 bar, for example, at high speeds, that 5 times higher speed, you'll have to inject it at 1250 bars. For injection, of course, in conventional systems, we used injector pump, mechanical injector pump, which is driven by direct connection to the crankshaft through a belt system or gear system or something, any system, and the cam inside create the pressure required depending on the speed. And of course, in this system, both pressurizing and delivery of fuel to the nozzle is done by the cam. Therefore, it happens at the same time. So it's a combined fuel pressurization and injection process. A cam-based mechanical system does the pressurization as well as delivery of fuel to the nozzle. So it's a simultaneous pressure generation and injection using a pump and an injector. So typically these injector pumps operate from 500 bar to 850 bar pressure. In common rail systems, which is the most common system that we find in modern diesel systems, of course, we use, there are two systems of course, mechanically operated, completely mechanical common rail systems as well as EFI systems. What is more common nowadays is computer controlled systems, that is electronic fuel injection systems. In common rail systems, of course, we keep the high pressure fuel in a common rail, so the rail is strong enough to keep the fuel at that pressure, at the required pressure. Therefore, the pressurization is done earlier, and the injection is done using an electrical signal whenever you need to inject. So the compared to the mechanical system, the injector pump system, where the pressurization and delivery of fuel is done at the same time, but in the common rail system, the pressurization is done in advance, and injection is done whenever it is required. Therefore, it's a separated process, separation of pressurization and delivery of fuel or the injection of fuel. And that itself make it a very useful system, because to control emissions, usually we do multiple injections in diesels, where we initially inject small amount of fuel, that is called pre-injection, to reduce noise and NOx emissions, and then the main injection takes place, and after that the post injection also a small amount is injected after uh, the main injection, that is again to reduce emissions. So I'll talk more about these things when I talk about engine emissions. So, so this is an advantage in common rail system, as it is a separated system of pressurization fuel and injection of fuel.